This is a vitamin? What? Oh, so this is the practice sheet for heat of reaction that you got in class. So I thought I would just go over it in case you have questions. Let's first define the symbols representing the data that we're using to determine the heat of a chemical reaction. First is this delta H sub F under standard conditions. The heat involved in a reaction when 1 mole of a substance is formed from its elements, that kind of reaction. And those elements are in their standard states, like H2 gas, that's an element, the elemental form, right? It happens to be a molecule in the gas. So that's every time you form a substance, there's some sort of heat involved, and it could be plus or minus. It could be an endothermic formation, it could be an exothermic formation. So that sign goes with the data. Now, BE, what's that? Oh, that's the heat required to break 1 mole of a particular bond type in the gas phase. So gas phase. So that's broken. So that's always going to be a positive number. Okay, so number 1 says, determine the heat of a reaction for the hydrogenation of ethene, whatever. Oh, here's ethene hydrogenation, adding hydrogen to it to saturate that single bond. Okay, using heats of formation data, that's this data, and then by using bond energies, that's the other piece. So we're going to do it 2 ways and see if our results concur. So let's first try the heat of formation data way. Okay, so this is a reactant, and the reactant is going to unform. So I'm going to unform whatever my data is for 1 mole of this C2H4. So let's see. I'm looking at this data, C2H4. So that's a positive 52.3 kilojoules. I'm going to unform this. And then that's in its elemental state. So the delta H of formation for that is 0. And then I'm going to combine that. I'm going to add to it C2H6. So C2H6, right? So a negative 84.7 kilojoules. There. So this is going to be a negative 52 combined with a negative 84. So we're going to get a negative 137 kilojoules. So that is the delta H for the reaction under standard conditions. Okay, now let's try the other method. Let's use the bond enthalpy method. Okay, so this one's going to require a bit more work because I have to examine each of the bond types. I know I've got the CH bond type and a C double bond C bond type in this one. So CH, I got 1, 2, 3, 4. I got 4 of those, and each of those are 414, and then my C double bond C is a 612. So 414 kilojoules. Add to that just 1 of these, and that's 612 kilojoules. And then I have an HH single bond there. So I'm going to add to that 436 is what the data is. And then that's all the energy required to break the bonds in the reactants. But now I'm going to have to I'm going to have to change the sign of the data here in the product. So I've got 6 of the CH bonds, 6 of those, and that's 414. And I'll combine it with my carbon-carbon single, which is 347. Okay. So it looks like this whole thing here is 2704 breaking bond energies. And then I'm going to make, meaning I have to reverse the sign of these bond energies, which total 2831. Yeah, so I'm going to get a negative number here, negative 127 kilojoules. That's the heat of the reaction that's predicted from this method. And I can't say it's under standard conditions because the data is not under standard conditions. So the best I can do is just calculate a delta H. Hey, these two numbers, they're not too far off, I guess because everything's in the gas phase, but I'm not standard, and these are average values, so we don't expect them to be exact. Okay, so that's the two methods. This one's not as good. So in our next question here, we're just doing a standard heat of reaction. It looks like we've got some formation data, so we'll just do the one method. So how do we do that? Well, we have to unform the reactants, and then we have to form the products. So unform means we're going to have to change a sign. Now my first reactant here is a liquid diatomic bromine, so that's an element here in its standard state already. So there is no formation energy involved there. So that's just a 0. And, oh, hydrogen, just like up here, that's just going to be a 0. So it looks like I've got to unform 2 moles of hydroxide. Oh, here's the data for that. Okay, so that's done. And now I'm going to add to that, let's see, 2 bromide ions. Here's the data for that. And then add to that 2 H2O liquid. Oh, yeah, here it is. Negative 285.83 kilojoules. All right, so I got to add that up. So this is going to give me a positive 660 and then a negative, double that, and a negative, double that. Overall, I get a negative 354.86 kilojoules in the calculator, but I only have one decimal place in these additions, so I better just report negative 354.9 kilojoules. So that is the standard heat of reaction for this reaction. And that's a very accurate value. Okay, let's continue practicing that method here with this reaction. Well, if I'm just going to use delta H of formation stuff, I know that this aluminum is solid. It's in its standard state. That's not going to be involved. And the carbon solid graphite, that's not going to be involved. Oh, look, the overall heat of reaction is written there, just like we had to calculate up there. So this is a different question. Find the heat of formation for this this substance. So it's like, it's unforming, and there's 2 of it. So that's like X right there. And then I'm going to add to that 3 times the heat of formation of CO2 gas. What is that? It's a negative number. Negative 393.5 kilojoules. So I got 2 moles of this X times 3 times this is equal to the overall 2170.9 kilojoules. Okay. So if we combine that, it looks like we're going to have to bring that to the other side. We're going to have to divide by 2. Negative X comes out to be 1675.7 kilojoules per mole because I'm dividing by the 2 moles. So that means X is negative 1675.7 kilojoules per mole, and that is delta H of formation under standard conditions of aluminum, this particular aluminum oxide, given this data. So there's our answer. Very nice. Okay, so for this one, it looks like, oh, we're using this reaction here. We've got 5 grams of aluminum, and we want to know about the heat involved when we're producing this 5 grams of aluminum. Well, we have the heat involved when we produce 4 moles of aluminum. So let's turn the 5 grams into moles. 1 mole of aluminum from the periodic table, 26.98 grams. Okay, so grams cancel. And we got 1 mole. Here's the heat involved, positive 2170.9 kilojoules for every 4 moles of aluminum. So moles cancel, and that gives us our kilojoules, 100.6, because I got 4 sig figs kilojoules. There. Very nice.